This week in this chapter we will discuss about diodes. So in order to cover uh, not completely but sufficiently on diodes, we will discuss the content will cover three things. The first one is to cover the construction of PN junction, which is the base that make a semiconductor diode. And then secondly, in the chapter we will also cover the and be familiarized with the diode equation and the characteristics, the equation and its current and voltage characteristics. And then finally, we will try to look into application circuits that use diodes, right, and analyze them, analyze these various circuits where the semiconductor diodes are used. So basically, there are two types of circuit. The first one we look into a simple circuit utilizing diode, and then in second part we will see what we call a rectifier, which are divided into two: half wave and full wave rectifier. So let's start this chapter. Before we start, we'll look into the background of diode. So sometimes we get curious about the word diode. The term diode itself has been used for the first time by William Henry Eccles in 1919. So this is a picture of William Henry Eccles. Basically, he one of the pioneer in the radio communication technology. And what he used was, at the moment, it was it wasn't the diode that as we have today. It was a glass tube, vacuum tube with a cathode and anode. So he called it diode. And since two poles component that have cathode and anode are called diode, right? So what does diode means? Diode is come from Greek words di and ode. Di means two, ode means electrode, right? So and the electrodes are called anode and cathode. So that's a bit of background on the terms diode. So where do we use diode today? So there are a lot of types of diode. There's many type of diodes, right? So here I list several examples that we are probably familiar with, where we can see them in daily applications. So the first one is the light emitting diode, or LED. So we've seen this in displays, in signals like the traffic lights, in illumination for decoration, and even in television. So this is a sample of the LED technology used in our television, right? And the second one that is used a lot is photodiodes. So photodiodes, what is it? It is a kind of diode that used as light detectors. So this is a sample of photodiodes. It is sensitive towards photons, basically towards light. It receives lights and it will react to that light. So it's used in light detectors, right? So we have many light detectors today that operates probably our home intelligently, and we also use it in sensors, for example, in communication. And finally, the thing that all of your lecturers are familiar with is the laser pointer. So in a laser pointer, what they have inside it, some of them have what they call a laser diode. So they use as pointers, and they use also as security alarm. So as you've seen in movies where there are lasers in front of a safety safe, for example, that is basically laser diode used in a security alarm system. So what is the basic component behind diodes? How does it constructed? How do we construct a diode? So a diode is basically a PN junction. So it's a material that is formed, a PN junction is formed using a semiconductor material. So what is a semiconductor material? A semiconductor material is basically a material that have 4 valence electrons. If you remember, 4 valence electrons means it has 4 electrons at the highest level of energy at the most outer circuit of its electron. It has 4 electrons, right? So P and N are different materials. One is P, one is N. So right, about semiconductor materials. In periodic table, if you want to look for semiconductor materials, there are materials basically that has conductivity, I would say, in the middle. So those who are in red in this periodic table, The one that is marked in red are basically the one that have a very high electrical conductivity. So electrical conductivity in Siemens per meter. It shows how much, how easy does that component or does that element conduct electricity. So for example, we can see here in very dark red, we see copper, we see silver, and our room is basically it's gold. So these three elements, along with aluminium, conduct electricity extremely good, right? And there are other components in blue or in light yellow. Those are the components that doesn't conduct electricity at all, right? It is dielectric basically. So and then we have also the component that is in the middle, around in orange color. So basically here is the component in this line is the component with 4 valence electron, and the components that we're using the most for semiconductors is Si and Ge, which is silicium and germanium, right? So the semiconductor material, this silicium and silica and germanium, what do we do with them? What do we do if basically they have initially the silicium. For example, we take an example of silicium. Silicium has basically at the beginning 4 valence electron, which are stables. What we do with them is basically we dope them. I mean, we inject them with impurities. The impurities being boron or phosphorus. So depending on which impurities you introduce into the semiconductor, you will create either a P material, a P region, or N region. If you look here, basically if we inject a boron, boron is basically a material with 3 valence electron. When it is injected into the semiconductor, what it creates is basically it creates a free space where an electron can move in. So this free space is what we call holes. So by injecting boron into silicium, into semiconductor, we create a p-type. So we create a holes where electron can move in. That's what we call a p-type. On the other hand, when we inject it with phosphorus, phosphorus basically has 5 valence electron. When we inject with 5 valence electron, what we create is we create a free electron that can move around, right? That can be transferred across the material. So when we have an extra electron, a free moving electron, that's what we call N-type. So N-type with free moving electrons, P-type with a moving holes. We call it holes because we have less electron. But again, of course, these two materials, P or N region, are both neutral. It's just that they have holes, or either in N-type they have extra electrons. So P with extra holes and N with extra or free electron that can circulate. Right. So what is the working principle of a diode? Diode is basically a combination of N-type and P-type. So what we create is, in the middle is what we call PN or NP junction, right? The free electron basically from the N-type will move to the junction to try to fill in the holes on the p-type, right? As they fill in the junction, what they create is they create this region where the holes, there's no more holes in the middle region. This region on the junction of the P and N type material is what we call depletion region, right? This depletion region creates a barrier potential that oppose basically further migration of N to P. So as this electron moves into holes near the junction, it creates the barrier, and this barrier creates a barrier potential. So this barrier potential is very important in diode. In diode, it creates a characteristic that we keep using after this. So let's see. So a diode, how does it work? It works in two conditions. It can work either in what we call forward bias or reverse bias. So what is forward bias? A forward bias is when we connect a voltage supply in this configuration. So what does it mean? It means that we connect the anode or the positive, the p-type junction with the positive terminal of a power supply, and the negative, the n-type junction with the negative terminal of our supply. This is what we call forward bias. In forward bias, what happens is the voltage, the electrons from our power supply will circulate into the p-type junction, right? Into the p-type junction, and will try to cross the PN junction. When they try to cross the PN junction, as previously mentioned, we have a barrier potential, right? We have barrier potential. The current can only pass the barrier if the voltage that we supply to the diode is larger than the barrier voltage. So this voltage that we need to overcome is what we call a forward bias voltage. A forward bias voltage. So a diode have a forward bias voltage. So what's the level, what's the amplitude of the voltage that we need in order to make the current go through a diode in forward bias? The voltage, well, it depends on the material of our semiconductor. Just right now, I've mentioned there's two type of semiconductor materials that we use a lot, either silicium or germanium. So at least if we construct our PN junction using silicium, we will have a bias voltage of 0.7 volts, and if we have germanium, we use germanium, we would have bias voltage of 0.3 volts, right? So it means that in order to be able to conduct currents, we have to at least the voltage that we're supplying has to be larger than 0.7 or 0.3. Okay, so basically a remark can also be made here. In this circuit, basically we only have diode connected to power supply. So for the circuit above, once the voltage supplied is larger than the bias voltage, the circuit is closed. Circuit is closed means the diode now conduct the current. It becomes just like a conductor without any resistance. If there is no resistance, then we can imagine that the electron that come out from the positive terminal of the power supply goes directly into the negative terminal of the power supply without any resistance. It means we're creating a short circuit. So that's not what we want to create, because we don't want to damage our power supply. So basically what we do is we add a resistance. So if I can change into a pen. So basically what we do is we add a small resistance to make sure that a short circuit will not happen, right? So a resistance is needed to limit the level of our current. And then in opposite direction, if we connect now, let me get my pointer. So if you connect now in opposite direction our power supply, where we have our positive terminal connected to n-type and n-type junction, and the negative terminal connected to the p-type junction, what will happen is that this is what we call connection in reverse bias. If it is connected in reverse bias, the free electron in n-type will go to the positive terminal of the battery. The same goes for the holes in the p-type, goes to the negative terminals of our power supply, thus creating a larger barrier potential. So we create larger barrier potential. So the area where we have barrier potential is what we call the depletion layer. So the depletion layer increase, therefore the current will never be able to pass, except for very minority charges that we call minority charge, right? So if it is connected in reverse bias, the current will never be able to goes across the diode, right? So from that explanation of the basic the basic of PN junction and the behavior of that PN junction that creates that bias voltage, we can therefore deduce a characteristic of a diode. So here we have a symbol of a diode. So the anode is noted as positive terminal and the cathode as negative terminal, and we show the direction on which it is forward biased by the direction of the arrow, where it will conduct current in this direction and not in the opposite direction. So if we look into the curve or the characteristic of voltage of diode versus, the current across the diode voltage versus the voltage of the diode, what we can see is that as we supply voltage to the, so here is 0, as we supply positive voltage or in forward bias, I would say, in terms of diode, if we supply a positive voltage, what will happen is the voltage, there will be no current. So basically there will be no current circulating in the diode unless it achieve this VD0, right? This VD0. So this VD0 is just a model representing the real behavior. The real behavior is basically it will increase gradually. So in the middle here would be basically the bias voltage of either 0.7 or 0.3 depending on the semiconductor, right? This is the real curve, a more accurate curve, but usually in order to just model the diode just for utilization, we say that the current will cross the diode once it attain VD0, what we call bias voltage or cut-off voltage, right? So VD0, how much how much is VD0? VD0 is for silicium is between 0.6 and 0.7. Usually we just take the value of 0.7 volts. So here it is explained for VD equals to VD0. VD equals to VD0. Once we have VD equals to VD0, diode is on. Therefore, we have currents. Unlimited. So it is now short circuit unlimited and very large amount of current circulating across that diode. But if we have VD smaller than VD0, the cutoff or the bias voltage, if it is smaller than the bias voltage, then the diode is off, right? So this is what we call the current voltage characteristic of a diode. So the important criteria that we want to remember for the analysis and utilization in the future slide is that VD0 will take equal to 0.7, and if it is larger than 0.7 it will conduct, lower than 0.7 it will not conduct. If we go into a larger range of voltage, basically it's not just positive voltage, we can also go into a reverse bias region, negative voltage, right? So here, once it is on, this region is what we call forward bias region, where we have the diode functioning normally. If we supply the voltage in the opposite direction, in reverse bias region, what happens is the diode will not be switched on. It doesn't conduct any current. It may conduct a very small current, as what we call minority charges just now, but usually it is neglected as it is very small. But as we supply more and more current in the reverse bias region, we might fall into a condition where we will go beyond the depletion region. We will go beyond a certain, if we goes beyond a certain value of voltage, what will happen is what we call a reverse breakdown region. So we will completely goes across the depletion area, and the current will also, basically the diode is just broken and it just conduct electricity, and there's no opposition anymore to the current. So now that we have seen the construction, basically we have seen several types of diode, its application, and we have seen the construction of it using the PN junction, as well as the most important thing, the characteristic of current voltage of a diode and the existence of that bias voltage, or sometimes called cutoff voltage. Now we can look into the application inside several type of circuit where we usually use diode, right? So, and we will also analyze the operation of that diode inside those circuit. To do so, we'll look at I would say two type of circuits. The first one is simple circuit, and the second one is rectifier circuit. Simple circuit, we'll see limiter function and clamper function using diode in a circuit. And second part, for rectifier circuit, we look at half wave rectifier and full wave rectifier. So I will explain more precisely in the next slides. So the first one, we'll start with the limiter circuit. So in the simple circuit using diode, there are two, limiter circuit and clamper circuit. So we'll start with limiter circuit. What is a limiter circuit? A limiter circuit is a circuit that is also sometimes called as clipper. So what does it mean by clipper? Clipper means that it cut out or it limit the input voltage. So on the output voltage, you will see basically a limited input at certain area, and the limiter is basically is reflected with a certain bias voltage as well. And here are basically two topologies of limiter circuit. On the top, what we have here is a positive voltage limiter, and at the bottom what we have is a negative voltage limiter. So a voltage limiter basically is also a rectifier, but it's just in terms of, if we look at it alone simply, we will call it as limiter or clipper, right? So in a positive limiter, what happens is basically when we put the diode in this particular direction, where when the input voltage is on the positive side waveform, the position of the diode is basically in forward bias, where it will conduct currents. So it means in positive direction, it will conduct currents. When it conduct currents, what does it mean? When it conduct currents means if the current arrive at the node A, so the current have two choice, either to go into the diode or to go into the load resistance. If the diode is on, I mean if the diode is basically in forward bias, then current can go through it. So the resistance is very, very low. So all the current will go through the diode. So the diode become a short circuit, a closed circuit. So all the currents will go through the diode in this direction. If it goes in this part of the circuit, it means there will be no current going into the load resistance. If no currents go into the load resistance, it means if we measure voltage across this resistance, the resistance will be 0. That's why we call it as limiter or clipper. So it clip this part of current, so you can you have no current at all. But to be more precise, to be more accurate, it won't be exactly 0. Why? Because basically across the diode, in order for the current to be able to go through it, there is the bias voltage that we need to overcome. So we will see basically a small value of voltage of 0.7 volts, right? So this is the positive limiter. And the negative limiter is basically the opposite of positive limiter, is when we put the diode on with the opposite direction, right? If you look into positive limiter again, if you come back here, what will happen when the input signal goes into the negative part of the waveform? If it goes into the negative part of the waveform, now the current goes in the opposite direction of what have been shown here. If it goes in opposite direction, it means it will encounter the diode in reverse bias. If it is in the reverse bias, it means it is an open circuit. Now the diode is an open circuit, so no current can be conducted through the diode, so all the current will be conducted through RL, right, through the load resistance. So the circuit is now, the current now goes through the outer part of the circuit. If it goes through the outer part of the circuit, it means now we will measure, if we measure the voltage across this resistance, the voltage will follow the form of the the sinusoidal waveform, but of course the value will be lower. Why? Because what we can see here, we have a load resistance here and we have R1 here. Basically, V out is a portion of the V input, because what we have here is basically a voltage divider, right? So the same is applied for the negative voltage limiter. So that's what a limiter circuit is. So this is a simple limiter circuit. So here we have an example of an exercise of a limiter circuit using diode. As you can see, we have a negative limiter. What does it mean to have a negative limiter? It means, okay, now we have an input of plus minus 10 volts sinusoidal waveform. Negative limiter means it will limit the negative part. Why? Because when the input goes through the positive half of the waveform, the diode is in reverse bias, so the current cannot be conducted through the diode. All the current goes through the load resistors. So that's why we can see the positive part is being reflected in the output signals, output voltage, where it is basically the output voltage is across the load resistance. And as the input goes to the negative half of the waveform, now the current will circulate in this direction where the diode is in forward bias. When the diode is in forward bias, mean the current will circulate short circuit in the inner part of the circuits. So no current goes through the load resistance. When no currents go through the load resistance, it means that at the output we won't observe the sinusoidal waveform, right? That's why we have this flat part of the output waveform. And again, of course, we have to take into account that there is bias, right? There is bias. So the bias of 0.7 volt in the direction of the forward bias has to be deducted here. So that's why we have a flat part of the output waveform at minus 0.7 volts. And then if we want to know the value of the peak voltage at the output, the peak voltage won't be 10 volts, right? It will not be 10 volt, because as it conducts through the load resistance, it goes through two resistance, R1 and RL. And R1 and RL is basically in a configuration of voltage divider. So in order to find the output voltage, it's basically the output voltage is the load resistance divided by the sum of resistance R1 plus RL, where we get 9.09 volts. So the peak voltage is at 9.09 volt, and we have only the positive half of the sinusoidal waveform. Okay, now instead of having just diode, what we can also introduce is basically we can introduce what we call a bias. So it's not, now the bias that we call is not the diode bias, but it's a bias, a DC current that we add in series with the diode, right? What is the purpose of adding a bias, right? What is the purpose of adding a bias? Adding a bias serves to basically to increase the level of the clipped or the limited voltage. For example, if we didn't add any bias, the clipped part or the limited part will be just at the value of the bias voltage, which is 0.7. But if we want to increase that clipped or limited value, what we can do is we just add a bias in series. Basically, it's a voltage in series with the diode, right? So limit voltage level can be adjusted by adding a bias voltage in series with the diode in reverse bias, right? So here it put in reverse bias mean the positive is at the cathode of the diode, and the same goes for here. At the anode, you put a negative terminal of the voltage bias. So now what will happen if instead of putting it in reverse bias, we put the bias or the DC voltage in forward bias. So now forward bias means we put the positive terminal of the voltage at the anode, and the same for positive limiter or negative limiter, we put it in what we call forward bias. So if we put it in reverse bias, which is the opposite of this, if we put in reverse bias, the bias is basically added to the clipped or to the limited voltage part, right? So we add it, for example, instead of being 0 here, we add it to becomes at minus 0.7 volt plus a certain bias. But now if we put the bias or the voltage in forward bias, what will happen is basically we add the bias on the opposite side of the clipped voltage. So if we clip a limit over here and we add the bias in forward bias, we basically add that level of bias voltage on the opposite side. So now we have basically an apparent DC voltage, something that looks like DC voltage here, which is equals to the V bias that have been added before we get into the sinusoidal form of the positive half wave. And this is for a negative limiter because we limit the negative part, right? As for the positive limiter, it's the same thing. If we add the bias in forward bias, when it means what it means by forward bias is that now we have the negative side connected to the cathode. So again, the same thing happens. So the clipped or the eliminated part will now be added with the bias. So we have minus V bias plus 0.7. So we observe the same kind of waveform, but in positive limiter is only the negative part that can be seen. Right? Now let's look at this example of exercise and try to solve it part by part from time frame to time frame, from half wave to half wave, right? So what we have here is basically two diodes. In regard to the positive direction of the waveform, diode D1 is in forward bias, diode D2 is in reverse bias, and we have basically a bias voltage added to D1 and D2 in reverse position, right? In reverse position. So what this means is basically we'll see from for example from time t0 to the half wave where we have positive side. So the voltage will go across in this direction across R1 and then it arrives to node 1. So it have two possibilities whether to go into D2 or D1. It can only goes into D1 because D2 is basically in reverse bias, in reverse position, so it cannot goes into D2, it can always goes into D1. But when it goes into D1, in order to be able to go across D1, it has to pass the voltage bias of the diode, which is now we can consider at 0.7. But it's not just 0.7 that it has to go through. It also have the bias added to the diode at 5 volts. So it has to go through 0.7 plus 5 volts. So it need to go through 5.7 volts before it can cross the branch. So what we'll see in output is basically the same point A and let's say the ground here. So we'll see that at output the voltage will increase until it reach 5.7 volts. When it reach 5.7 volts, what happened is the current can go through it, and now the circuit become closed, right? So that's what we're observing here. As the input current goes up, the voltage output also goes up, but once it reach 5.7 volts, now what happened is the current now can go through D1, so it goes through D1. If it goes through D1, now it means it is a short circuit, so no currents, no voltage at all that is observed. It is a short circuit, so now we observe a flat at 5.7 volts, right? A flat at 5.7 volts. And the same things happen for the negative part of the waveform. So another thing that might be interesting for us to look at in a bias limiter circuit is that we can also, if we look into bias limiter circuit that we've seen in previous slide, the bias voltage that we have here is basically fixed at V bias. But we might also want the bias voltage to be adjustable, right? So in order to make it adjustable, what we can do is the bias voltage can be created by a voltage divider, right? Where the V bias now will be a portion of a V supply. Imagine if our V bias, so V input is still V input, but instead of having one constant V bias can be adjusted by the ratio of voltage divider. So we can have the bias connected to a power supply, but then adjust the value of V bias by using a voltage divider, right? So now we might have a positive limiter here or negative limiter with the bias adjusted by R2 and R3, or better, what we can do is adjusting the V bias using a variable positive limiter. Here is a positive limiter using a variable limiter. It's basically using a potentiometer to adjust the voltage divider so that the V bias will be a portion of the V supply. So now we have an example where we use, instead of a constant V bias, now we have 12 volt at V bias, but V bias is basically we want to use just a portion of that 12 volt. So V bias is the output of this voltage divider, which is R3 divided by the sum of R, which is R3 plus R2. So V bias that we have is only, basically, instead of having 12 volt constant, we have an 8.2525 volt. And as we can see here, we have the circuit that we have here is a positive limiter. It means that when it has a positive half of the waveform, the diode conduct, thus giving a flat part, thus limit the voltage, so that we can only see the, so now what we have is only the negative part of the negative half part of the waveform, right? So here the waveform are the same. It's just that now we will be able to adjust the bias by using a voltage divider. Another interesting application that use diode is what we call a clamper circuit. So what is a clamper circuit? A clamper circuit is also known as DC restorer. So what it does is basically it add a DC component to an AC signal, an AC waveform. So what happens is, if in input you have a sinusoidal waveform that has a zero average, at the output of your clamper circuit, you will have the same sinusoidal waveform, but it is now translated with a certain amount of DC shift, right? So now it have a DC shift. You have translated everything into positive side. So when you translate everything onto positive side, your signals into positive side, it's what we call positive clamper. You can also translate it into the negative side, right? Shift it with a DC shift into the negative side. When we do this, this is what we call a negative clamper. So how do we make a clamper circuit using diode? Well, we need another component to help us. The component that we need is capacitor. So capacitor is placed here, right, in the circuit. And one properties that of a clamper circuit is that it doesn't change your waveform. So your sinusoidal waveform will be can be retrieved here. It's the same waveform, as well as the peak to peak value. So the difference of V max minus V min are still the same at the input and the output, right? The only thing is that you have created a DC shift. In either in positive for positive clamper or negative side for negative clamper. In order to do so, there's one condition that is necessary. We need to have a time constant RC larger than the period of the sinusoidal waveform. What is the time constant RC? Basically, in a circuit with RC, with resistance and capacitor, the product of R multiplied by C is what we call a time constant. A time constant is basically the period that it takes for the voltage to be stabilized or saturated in a capacitor. So this this time constant need to be at least tenfold or at least 10 times larger than the period of the sinusoidal waveform. So the next thing that we can see here in the output, the shift, the DC shift is basically DC shift is the V output equals to V in, and the V in minus 0.7 volt. V in minus 0.7 volt here is basically the VC, the voltage of the capacitor as it is charged by the power supply, right? And we have the minus 0.7 volt, of course, because by now I think you all understand that it is because we have added the bias of the of the uh, of the transistor, right? There's nevertheless a remark that I want to have here. A remark is that the clamper circuit have the DC shift, so it maintains the waveform of the input only when it is in steady state. But in the beginning, when we switch on the clamper circuit, the voltage doesn't looks exactly like the input circuit, and it's not directly shifted with the DC shift. There's something's happening in the transient phase, and it is very well explained in this little video here by All About Electronics, on which I will put the link on the video as well. So now the next one in this section, what we're going to look at is the half-wave rectifier. So in half-wave rectifier, we're going to go through it by three parts. The first part, we will try to look at the basic concept of a DC power supply, because it is where the half-wave rectifier is used. And then after looking at the basic principle of a DC power supply, we'll look into the consequence of using a diode in this power supply. For example, we have to take into account the first one, to take into account the barrier potential, right? The barrier potential or the bias voltage. What's the effect on the output of the half wave rectifier? And then secondly, we will also take into account the application, or I mean the usage of transformer coupled input voltage, because what will happen is that the DC power supply is usually at the input of it, we have to step down the voltage from the wall socket voltage, which is around 220 or 240 volts, into a lower voltage in the DC power supply. So we have a transformer. So we'll see also how do we take into account the integration of transformer into our half-wave rectifiers. So what is the basic behind a DC power supply? What does a DC power supply do? What does it do is basically it converts an AC signals. For example, in our power outlets, we have either 110 volts or 220 volts. In certain area it's 60 hertz, or in certain other countries it's 50 hertz AC available at wall outlets into a constant DC voltage. So we're going to change from AC voltage to a DC voltage to be able to be used in an application that needs DC voltage, right? So to do so, we use a rectifier. So rectifier function is just to convert the AC input into a DC input. So here what we have is basically it's a simplified rectifier. It's a very basic rectifier where the only components that we have in it is a diode, right? So what happened when we have only a diode? What happened is basically when we are in a positive part of the waveform, if the diode is in positive bias direction configuration, what will happen is in the output it will continue to conduct the signal, and the signal will look just like the signals in the input. As the signals goes into the negative part of the waveform, the diode will basically oppose to the direction of the current, and it cut off the current, doesn't allow the circulation of the current on the opposite direction. So at the end we only have in a simple rectifier, what we have at the end is the pulse on the positive side. But in a more complete DC power supply, we would have not just rectifier, it's a combination of rectifier with other component, because with only rectifier, we will have a pulsing signal. Of course, it's on positive side, but it is still pulsing. In order to be able to make it a smooth DC signal that can be used by our application, we need several other components. So after the rectifier, what we need is basically a filter. What does a filter do? The function of the filter is to eliminate any fluctuation. So basically here we have fluctuating positive signals. It eliminates that fluctuation and rectify it into a smoother DC voltage. And then of course we have a regulator. Regulator is basically a set of circuit where it maintains a constant voltage and it let us varies or change that value of voltage. So a regulator, if for example our load need a higher voltage, it can change the voltage to a higher level. If it needs a lower voltage, then it will change the voltage to a lower level. And of course here we are going to concentrate only on rectifier, which use the diode that we discussing in this chapter. Whereas for filter and regulator, there are more other components in it that will not be discussed in this chapter. So a half-wave rectifier. So as I've explained just now, basically what happened is if in input we have a sinusoidal signal, when we go through the first part where the waveform is on the positive side, when the diode is basically on a positive bias position, it will allow the current to be conducted through the circuit and get into the load. So across the load resistance in the output, we will observe the same signal as in the input. Whereas in the second time, from T1 to T2, when the input signals goes into the negative part of the waveform, what will happen is basically the current tries to circulate back into the power supply in the opposite direction of the diode. So it is now in reverse bias. So there will be no current conducted. It is opposing the direction of the current. Direction of diode is in opposition with the direction of the current. So there's no current that will be circulating in the load. So the output voltage that is observed across the load will be equals to 0 from time T1 to T2. So in summary, from times T0 to T2, we will observe the half of the waveform on the positive side, right? So for this kind of waveform, we can calculate an average voltage, because if we know that the frequency is quite high at 60 Hz or 50 Hz, from a point of view of application, sometimes, for example, like our lightning application, our lights, what happen is it can see only the average of the voltage. So if you want to calculate the average of the voltage, basically across the period of 2 pi, the average voltage is the V maximum, called Vp, divided by pi. So that's the average voltage that is seen from the point of view of the load, right? So one precision that we may want to take into account is that the P or the voltage, the maximum voltage here, now we are considering that Vp or voltage, maximum voltage, will be equals to V input. Whereas we know that a diode, in order to be able, in order for it to be functioning, V input have to be higher than the value of 0.7 volt or 0.3 volt, depending on the semiconductor that we use, right? So there is that cut-off voltage, that bias voltage, that need to be overcome. So basically the Vp is not totally V equals to V input. Vp in reality, if you want to consider the bias voltage, should be equals to V input minus the bias voltage, which is in the case of silicium, germanium, it will be equals to 0.7 volts. So here we have an example of the calculation of an average voltage as a signal of a 50 volt sinusoidal goes through a rectifier. So the average voltage is, of course, it's the Vp divided by pi. So 50 volts input signal divided by pi becomes 15.9 volts. So you notice that if we calculate, basically in reference, when we compare to the maximum voltage, the average voltage that is received or can be seen from the point of view of load is basically is 31.8% of the maximum voltage given in the input, right? In terms of DC, is 31 point I mean the average after rectifying is 31.8%. Here we have another example where we have two rectifiers, right? Two rectifiers, where one we have an input of plus minus 5 volt, the other one is plus minus 100 volts. Going through a rectifier. Here we have the resistance load. So we measure the output voltage across the load resistance. Here what happened is that in this particular case, we are going to take into account the bias voltage. So V out, VP out equals to V in minus the bias voltage. So for in the first case where we have plus minus 5 volts, the output voltage will be equals to 5 minus 0.7 volts. So we consider the bias voltage as 0.7. And in the second case, it will be 100 minus 0.7, which is equal to 99.3 volts. And both of them have the same form, of course, because the rectifier only eliminate the negative part of the sinusoidal waveform. A half-wave rectifier is, however, never used alone in DC power supply. Because in a DC power supply, what we do is basically we need to create an isolation between the supply and the application. So we use a transformer coupled with the AC input voltage before we get into the rectifier. So we separate between the input from the wall socket with the application that we want to use, or from the rectifier itself, right? So the isolation is made by transformer. And transformer is a chapter that we've seen before. So basically, we doesn't introduce any other complication or any other complexity, rather than just what we need to do is just integrate the fact that there are factors of transformer over here where the voltage could be changed. The frequency, again, in a transformer, the frequency stays the same, constant, but the thing that's changed is just the voltage between the input and the output. So now let's go through the text first. Transformer coupling provides two advantages, right? As I said just now, it allows the source voltage to be stepped down as needed. So basically, from 220 volts into our application, the DC power supply might probably just need 12 volts or 10 volts. What happens is we're going to use the transformer to do the step down. And secondly, as I mentioned just now, it is to isolate the rectifier from any short hazard of the supply, right? So in terms of calculation, the VP out is still the same, right? The voltage at the output of the rectifier, of course, the maximum voltage, the peak voltage of the half wave of the output of the rectifier are still the same. Is equals to V maximum or VP minus the bias, which is 0.7 volts. But now the only thing that we need to take into account is this VP or V maximum is a V maximum at the output of the transformer, which means it is the V output at the secondary. And if you want to compare it with the voltage of the power supply, we know that in a transformer, we might define a ratio of N, which is the ratio of the number of turns of the secondary coils divided by the number of turns of the primary coils. So the V secondary will be equals to a multiplication of N of this ratio multiplied by the V primary, right? For example, if N is a number larger than 1, it means V secondary is higher than V primary. It means it's a step up. But what we usually have is N is lower than 1 to step down the voltage. So we have a V secondary which is smaller than the V primary, right? So that's the only thing that we need to take into account, that V secondary or V at the across the load is V secondary, which is N multiplied by the V primary. And if we want to make it accurate, the V at the output or across the load has to be we have to we have to take away the amount of the bias voltage as well, right? So here we have an example of the application. So imagine if we have in input a sinusoidal waveform with a maximum voltage or peak voltage of 156 volts, and we have a ratio of the transformer stepping down ratio of 2 to 1. So what does it mean? It means that at the secondary, what we'll have is we have half of the voltage of the input. So if we have 156 at the input, half of 156 means at the output or at the secondary of the transformer we will have 78 volts, and what we're going to rectify is basically a sine wave that has a maximum voltage or peak voltage of 78 volts, right? So the voltage, the half wave rectified voltage in the output across the load resistance is therefore 78 volt minus the bias voltage of our particular diode. Here the bias voltage is 0.7 volts, so it means we have at the output across the resistance load resistance a voltage of 737.3 volts. So now that we have finished the section on half wave rectifiers, I think we can note that the main inconvenience of the half wave rectifiers is that the average voltage is much smaller than the peak voltage. So in order to be able to capture a higher level of voltage when we go through a rectifier, instead of using a half wave rectifier, what we can do is we use a full wave rectifiers, right? So in this section we'll go through full wave rectifiers by going through 2 points. The first one is the center tap full wave rectifier, which is one type, and then the other type that we will try to explain is the bridge full wave rectifier. So the advantage from using a full wave rectifiers instead of half wave rectifiers can directly be seen from the form of the output waveform, right? So if you imagine from the half wave rectifiers, what happened is we just eliminate all the negative part of the waveform, and we're left with only half part of the waveform. So everything on the negative part are eliminated. So the frequency still maintains the same, f is still f, but now in full wave rectifier, what happened is we do not just eliminate. What we do is basically we reverse the negative part of the waveform into the positive part of the waveform. So we have the signals across the whole period, 360 degree of the cycle, right? It means that we have now a frequency that has doubled. So instead of having just half and then nothing here, we have both part of the signals on the positive half, right? So we have increased the frequency. Increasing the frequency is not the advantage. The advantage is basically we have more power from the signal. So the result from the rectification is basically the main thing that is advantageous is that we have increased the average voltage on the output. So the average voltage on the output, instead of having just Vp divided by pi in half wave, now in full wave we have multiplied by 2 Vp divided by pi, which is now approximately 63.7% of the maximum or the peak voltage. So we have a much higher output voltage compared to a half wave voltage. So for example here, for an input of sinusoidal of plus 15 minus 15, on the output we will observe such signals, right? With the frequency, instead of having frequencies over here, now the frequency has doubled. Frequency has doubled means the period of the signals have shortened by half, right? And the average voltage for a plus 15 minus 15 sinusoidal waveform is 2 Vp divided by pi, which is 30 volts divided by pi becomes 9.55 volts. So it's double from the half wave rectifiers. The first type of full wave rectifier is what we call the center tap full wave rectifier. So what is the center tap rectifier? Before we start to look into what center tap means, we have to understand that just like in the last part of half wave rectifier, we know that in a DC supply application, we will always use a transformer for two advantages, which is the first one is to isolate the circuit, and second one to possibly step down the voltage, right? So we consider that we will use we're using a transformer. The center tap rectifier is means that basically we are tapping the voltage at the center of the secondary coils. So imagine, so we'll not explain the first part, the first circuit of the input is just a coil of primary and the input voltage. But now what's interesting is on the secondary part of the transformers. In the secondary part of the transformers, half of the coil of the transformers is connected to one diode circuit, while the other half is connected to another diode, right? So the waveform that's come out from the secondary coil of the transformers is divided into two. Instead of having V in, the full wave V in, is now, imagine if we have a ratio of 1 1. If the number of coil in primary and secondary are the same, it means that if we have V in at a certain value, V out will be at the same level of peak to peak voltage. But as we tap and divide it into two, what will happen is each half will have half part of the will have half of the peak to peak value. So it will have V secondary over 2, assuming that we have 1 ratio, right? So what will happen? What will happen is, if we look in the first part where we have the first half of the waveform from 0 to half of the period, when the voltage is positive, what will happen is, when you look at D1 and D2, is D1 which is D1 that is in position of forward bias. If it is in position of forward bias, so imagine the voltage circulating in this direction, and at the output of the transformer, it circulates in the same direction. So it's only through D1 that it can go through, right? So the first part will go through D1. So that's why, and on the output we'll see half waveform that resembles to V in, but the value of V out is only half of the V in. As we goes into the second part of the second half of the waveform on the negative side, what happened is now the current circulates in the opposite direction. So in the transformer as well, it will circulate in this direction. If we only have D1, it would mean that the current could not circulate, right? Because we have D1 in the reverse bias, but now what we have is it is divided into two, and we have D2 which is in forward bias. So the negative side of the waveform can also circulate to get into the load resistor. So we have also replicated the waveform of the negative side of the input waveform, but now it has been reversed into the positive side in the output. So what happened here is that we have doubled the frequency. We have both of them in one period of input, right? So let's take a look at what's the consequence of using the transformer, and what will happen at the voltage in the output. So imagine if we have 1:1 ratio. So the peak to peak input voltage will be now divided in the secondary into two parts. It will be the peak to peak on each part. On each half will be V peak over 2 and minus V peak over 2, right? So now the waveform, as I mentioned just now already, the V peak at the output is only half of the V peak in the input. And of course, if we consider as well to take into account the bias of the diode, which we can consider here at 0.7 volts, the V peak on the output will be equals to half of the V peak in the input, in the primary. If it is ratio 1:1, then it is also the secondary, minus 0.7 volt. So what is the consequence of this? The consequence of this is, if we want to have, for example, in the output, the voltage across the load resistors, that the peak value equals to the peak value of the input, it means that we have to increase the ratio. We have to increase the ratio by how many? We have to increase the ratio exactly by 2, because we're dividing by 2. So in order to be able to get the same peak to peak value, we have to have the same amount of coil on each half compared to the amount of turn of coil in the primary. So it should be 1, the ratio is 1 to 2 in order to be able to have Vp at the output equals to Vp at the input, V peak and input. The second type of full wave rectifier is what we call bridge rectifier. So what is a bridge rectifier? In comparison to a center tap rectifier needs us to basically tap the voltage in the middle of the transformer to separate it into two parts, right? Half and half of to divide the output voltage into half. Instead of tapping or going into the transformers, which is finely coiled, a better way to do it, or mostly used way, is basically this type of bridge rectifier. In bridge rectifier, we use 4 diodes that are mounted in such position. So the diodes are numbered as D1, D2, D3, and D4. So the numbers represent basically the two operating parts in regards to the half wave of the input signals. The first half being the positive parts of the waveform, and the second half being the second part of the waveform. In the first part, where we have a positive part, when the secondary voltage or the output voltage of the transformers comes into this circuit, it is D1 and D2 that conducts the current. So D1 and D2 conduct currents, means the current circulate in the direction that's shown in these red arrows, and it goes into the load. So here we have the resistance load. Therefore, when we measure the voltage across this resistance, we get this waveform, right? We get this waveform. In second time, when the input waveform is on the negative side, what we have is, now instead of having D1 and D2, we have now D3 and D4, because now the current goes in the opposite direction, and it is D3 and D4 that allows the current to goes into the resistors load, right? And producing, therefore, the other part, inverting the other part of the negative part of the waveform into the positive part, giving us these two waveform, therefore increasing the frequency to double of the initial frequency of the input signal. If you want to take into account the diode voltages, the thing again, if you want to take into account the bias of the diode, what we need to do is therefore to take into account the 0.7 volts at each diode, right? For example, in portion, in part of the time where the wave is the input wave is on the positive side, we have D1 and D3 working in series, right? So the current basically goes in this direction. It goes across D2 and D4. I'm sorry, it's D2 and D4. So it goes through two diode. Therefore, it need to counter the two bias voltage of 0.7, right? So V output will be equals to V peak of the secondary minus 1.4 volts. So here is so V, if we don't consider it in ideal diodes, then Vp will be to V secondary. That's all. But if we consider the in practical diodes where there is a drop of voltage due to the bias, then the V peak at the output, VP means V peak, at the output will be equals to V peak at the secondary minus 2 times 0.7 volts. So now after looking at the operating of the bridge rectifier that have transformed our sinusoidal waveform into only one-sided waveform that has double in frequency, the thing that we need to do now is to filter the signals. As we seen previously, in order to be able to get proper DC signals, we need to eliminate all the fluctuations. In order to eliminate the fluctuations, what we use is basically we use a filter, and the main component in a filter is basically the addition of a capacitor. So now here we show an example of a half wave rectifier. So for full wave rectifier, it will be the same thing. Basically, at the end of the diode circuit, we will add a capacitor. So what is the function of this capacitor? We call this capacitor as capacitor input filter. Capacitor input filter. So how does it function? As we look at the input voltage waveform, when it increase in the positive side, when it increase from 0 to V peak, what happen is the current circulates in the diodes and it goes into the capacitor. Therefore, the capacitor will be charged, right? The capacitor will be charged up to the value of V peak, and once it goes beyond the V peak, what happen is the input voltage start to drops, and the capacitor will see that, well, there is a voltage drop. If you remember the thing that we've learned in capacitor, the currents across the capacitor I equals to dVc over dt, right? So now that we have a drop, so that means we have a difference potential. We create a voltage, right? When there is a voltage, because Vc is V peak, but now V input drops, what will happen is the capacitor will start to discharge. So in this portion, when the voltage of the input start to decrease, in the output, what we observe is the capacitor will discharge all the charges that is stored to try to compensate that dV over dt. So basically what we see is, instead of having the waveform to drop to 0, we see a straight line. This straight line is basically the discharge of our capacitor. So now we have the form of the charging and discharging of capacitor that try to filter the waveform. So here we have half waveform, at the bottom we have full waveform. So the capacitor filter try to filter the fluctuation. So it gives a smoother, a more smooth waveform, right? A more smooth waveform. But if we compare between a half wave rectifier and full wave rectifier, we can see that the ripples are larger in the half wave rectifier compared to a full wave rectifier. Okay, what is ripple? Ripple is basically the amount of fluctuation that we can see. So amount of fluctuation is measured by this formula. The amount of fluctuation, or the ripple, called as ripple, is measured as the ratio of VRPP. So VRPP is basically the peak-to-peak ripple voltage. So what is peak-to-peak ripple voltage? It is presented here. Peak-to-peak ripple voltage is the peak-to-peak of the new rectified and filtered voltage. So it's this difference, right? Divided by VDC. And what is VDC? VDC is the average voltage of the now filtered and rectified voltage, right? So the ratio of this peak-to-peak ripple divided by the average voltage is what we call ripple. So the ripple is higher in half waveform, and it is smaller in full waveform. It's higher because simply because the capacitor has to be discharged longer. Therefore, the peak and the minimum the peak to peak voltage is much larger, therefore the ripple is also higher, right? So we can see that because the frequency of the full wave rectifier get higher, right? The frequency is increased by 2, so it is easier to filter. It is easier to filter means it is easier to get a lower ripple, right? So regarding this formula, so what is if we can measure, then if we can measure, then of course we measure the peak to peak ripple voltage and the average voltage. But in terms of approximation, we can also see in the next slide the approximation of this peak to peak voltage and DC voltage. So the peak to peak voltage can be approximated with this value, with this formula, which is equals to 1 over F RL multiplied by C, and all the fraction multiplied by VP rectified. So what are these parameters? So first, again, VRPP is the peak-to-peak ripple voltage, peak-to-peak ripple voltage. F is the frequency of the input signals in hertz. RL is the resistance of the load that consumes this voltage. C is the value of the capacitor of our filter capacitor, and VP rectified is basically the peak to peak, the peak voltage of is the unfiltered peak rectified voltage, right? Is the unfiltered peak rectified voltage. So previously, basically what we had, if I can change to a pen. So F is the frequency in hertz of the input voltage. R is the resistance of the load that consumes this voltage, so of course in ohm. And C is the capacitor in farad. And VP rectified is the unfiltered peak rectified voltage. So unfiltered means after rectification we have these signals. This value, this V peak, is what we call VP rectified, right? So this is this value. And for the average DC voltage, it can be computed and can be calculated, approximated to 1 minus 1 over 2 multiplied by F multiplied by RL multiplied by C, and all multiplied by, again, the unfiltered peak rectified voltage, right? So what can we conclude here? One thing that we can conclude is that if we basically what we want to do is we want to reduce, the objective is always to reduce the, I'm sorry, I'll go back to laser pointer. So the objective is always to reduce the ripple. If we want to reduce the ripples, it means that we want to reduce the peak to peak ripple voltage. So this is the equation of the peak to peak ripple voltage. If we want to reduce the peak to peak ripple voltage, it means we have to increase the value that we have, the magnitude of the parameters that we have in here. So it means if we increase the frequency, or if we increase the resistance of the load, level, and if we increase the value of the capacitor or the filter capacitor, we will be able to reduce the ripples. So again, increasing the frequency, that's easy. Increasing the frequency means we make the ripples have a higher frequency, therefore it's easier to filter. We've seen that. If we increase R and C, it means we also increase the efficiency of the discharging of the capacitor, right? So that's on a ripple ratio, on ripple that we really want to reduce. So here at the end we have an example of an exercise. So it's a very complete exercise that you can try. We can try to do it. So for example here the question says what it asks for is to determine the ripple of the filtered bridge with a load as indicated in the figure. So the load is 2.2 kilo ohm, right? And then the capacitor's filter is at 50 microfarad. And here we have a full wave rectifier, a bridge rectifier, right? Another thing that we have to also to consider is the ratio, the step down ratio of the transformer. Here we have 10:1. Okay, in order to start this, of course, we'll do it step by step. We'll look at the input first. And we know we have a primary transformer circuit and secondary transformer circuit. Of course, the first stage would be to find the V secondary, right? To find the V secondary, okay, we'll go here. So the ratio is 0.1, right? Because it is 10:1. But now what happened is the voltage that is given in input is not given as peak to peak. So usually what's given is peak to peak, let's say plus 100 volt minus 100 volt. But now what's given is an RMS value. So what is an RMS value? RMS value is also what we can call the effective value. What is the relation between RMS value and peak value? So RMS value is actually, so VRMS is equals to peak value of the voltage divided by square root of 2. Square root of 2, which is closely equals to 1.414. So that's why here, when they try to calculate the voltage of the primary, they multiply 1.414, which is the square root of 2, multiplied by the VRMS that's given. So basically, our voltage in input is a 163 volts sinusoidal. So 163 volts being the peak voltage. Okay, once that we know that, then we know that in V secondary, so Vp is the V peak of the secondary equals to the ratio multiplied by the V peak of the primary. So we have a ratio of 10:1, 0.1. So now we have reduced by tenfold the voltage. So now we have a peak voltage of 16.3 volts. Okay, now we have arrived here. The next stage is to go across the bridge. So the rectifier bridge. So the voltage here, the voltage after rectifier, in order to find the voltage after rectifier, we have to take into account the, if you want to be accurate, you need to take into account the bias voltage of the diode. And in each cycle, be it in positive or in negative, we have two diodes that we have to take into account. So that's when we have 16.3 volt minus 1.4 volts. So over here, V after rectification, at this point, we have now a voltage of 14.9 volts, right? 14.9 volts. The peak voltage is 49 volts. And the peak voltage of 14.9 volts is, of course, it is an unfiltered voltage. So it is something like that, with V peak equals to 14.9 volts. And the question asked at the end, what it asks for is, it asks for the ripple factor, R. So in order to calculate the ripple factor, we need, the first one is the peak to peak voltage of the ripple. And then what we need is the average voltage, average DC voltage. So this use the formula that we've seen in previous slide, right? The thing that's left for us to do is just to replace the value of frequency. So the frequency being, if we look here, it is 60 hertz, right? It's 60 hertz. And then multiplied by, why do they put 120 hertz? So it's 60 hertz. It should be 60 hertz, right? So it is 60 hertz. Multiplied by the resistors of the load. Resistors of the load is 2.2 kilo ohm. And then the capacitor is at 50 microfarad. So it gives us multiplied by, of course, the voltage after rectification, which we have found here. So the value equals to, of course, this is not the correct value because we have basically double the frequency. The frequency is supposed to be just 60 Hertz, but now it's written as 120 Hertz. So the voltage need to be multiplied by 2. The correct answer is 2.26 volts. And the same goes for the DC average voltage. So again, so here we just replace it with the value. So instead of 2F being 240, so it should be equals to 120 Hertz, right? If we do 120 Hertz, then we should obtain another value here. So to find the final ripple ratio, the ripple factor, that ratio, what we have to do is just take this value divided by the value that we found below, right? So we should find another value that is not this value, and then written in percentage is just multiply by 100. So that's all on the topic of diode. We've seen a lot of things. The first one being the PN junction and how it works internally, and then we have looked into simple circuit application such as clamper and the clipper circuit and clampers, and then we went to look directly into rectifiers. So we have two rectifiers, the full wave rectifiers and half wave rectifiers, and this being the last one, which is bridge rectifiers, and we have done even the calculation of the ripple ratio. So see you in the next chapter. Thank you.